article sheet from the last stream. So here you go. Train consists of locomotive 4,000 kilograms and 2 carriages, each of 2,000 kilograms. Going to give you 5 minutes to have a go at this question. Actually, it's a free on the about Simon watched it by Storm Mechanic. Yeah, we're doing this and Pulleys today. Finishing off this and Pulleys. Just simple ones. It's not simple. Then do all things in the same direction, minus all things in the opposite direction. Okay. 1 minute to go. Result A equals all the forces the same way, minus all the forces the opposite. Okay. Lags 8 seconds. Cope with that. Nobody ever asks any questions. 1 and stop. Right. Okay, right. That is enough time to do that question, believe it or not. One of the students in the classroom managed to get the answer out. So let's just put a little diagram in here of our train and our two carriages. So we've got, let's just assume we have a driving force going forwards to start with. And we've got our train has mass of 4000 G, and each carriage has a mass of 2000 G. Let's assume that the connecting ropes are under tension. So I'm going to call this one T, and then I'm going to call this one T1. Okay, and we've got a resistance force on the locomotive of 6,000 newtons. Sorry, no, 9,000. Mistake. And on each carriage we've got, so on this carriage we have got 6,000, and on this carriage we have got 3,000 newtons. We've also got reactions going on, so reaction 1, reaction 2, reaction 3. We are not going to actually need those reactions in this question. So, determine whether the locomotive is driving or braking. So let's just resolve on the whole system to start off with. So resolve on the whole system. And we'll resolve that way being our positive direction. So we've been told it's deaccelerating. So MA, so our A is going to be 2 in that direction. I'm going to resolve that as my positive direction. So therefore my MA will be negative in this case. Now on the whole system, I've got 4,000 plus 2,000 plus 2,000. So that will give me 8,000 times minus 2. So minus 2 times 8,000 is my MA. And as I'm resolving that way, D is going to be positive because I've assumed it's driving. And then I'm going to have a minus 9,000 here. And I'm also going to have a minus 6,000. And another minus 3,000. So those are all the resistances, 9,000, 6,000, 3,000. So that's my system resolved horizontally. So I've got minus 16,000 equals D, and we're going to minus 15 minus 18,000. And so therefore D comes out as 2,000 newtons. And as it's come out positive, I was correct in my assumption that it was a driving force. Therefore, a driving force. Force of 2,000 newtons. Now, if it had come out as negative, then I would have been wrong. It wouldn't have been a driving force. It would have been a braking force in this question. Let's just zoom that out a bit so you can see a bit more of my answer at the same time. So for part B, we want to find the magnitude of the force in each coupling. So what we can do is we can gradually resolve on each particle to find the tension. So let's just resolve on the locomotive. On the engine. So let's just resolve that way. So on that train, so we're going to have the acceleration here on this thing is going to be minus 2 times 4,000. Notice the minus 2 because that's my positive direction. It's deaccelerating, so therefore it's in the opposite direction. Equals the driving force minus this tension minus this 9,000. And we know the driving force is 2,000. So we're going to get minus 8,000 equals 2,000 equals 2,000 minus tension minus the 9,000. So therefore we are going to get the tension will be equal to 1,000 newtons. When we take that away, it gives us minus 10,000. Add that gives us minus 1,000, but minus equals a minus, so therefore it must be a plus. So therefore tension must equal 1,000. So it is in tension. I assumed a tension in the beginning, so therefore, as it's come out positive, it will be tension in my answer. Okay, there's a few murmurs in the classroom, unfortunately. If they haven't got that, they're wrong. Okay, so let's go to the first carriage now. Let's just zoom out so we can see the first carriage at the same time. Get rid of that. There we go. So let's look at the first carriage. So resolve on the first carriage. And we'll do the same thing. So again, we're going to do mass times acceleration, which will be -2 times by the mass, which is 2000. And that will equal everything in the same direction. So I've taken this as my positive direction. So I'm going to have the tension minus the second tension, T1, that's going the other direction, minus the resistant force in that direction, which I think was 6,000 newtons. Now we know this tension is 1,000, so I'm going to get minus 4,000 equals 1,000 minus T1 minus 6,000. So that's going to give me minus 5,000. When I add it to the other side, it gives me 1,000, but I've got a minus T1, so T1 will equal minus 1,000 newtons. So therefore, it's the opposite sign to what I got. So it's not tension, it's in compression. Okay, and it's not in tension because I assumed in the initial question that my force diagram that I was in tension. I got a negative value for my tension, so therefore I must be in compression. Any questions in the classroom? Okay. Moving on to the Pulleys questions from yesterday. So we got as far as there. So here's our first one for today. Let's just zoom that in a little bit. Question 3 on the Pulleys question, if you've got access to the sheets. You can get access to the sheets from the link in the video. Right, this is question 3. Let me just see how many minutes I'm going to give you for this. I don't think it's a huge question. I think it's about 3 minutes. I'm going to give you 3 minutes from now. You've had a bit of reading time as well. By the way, I've put the link to your channel in the use mic. Okay, 3 minutes is up. So let's look at this question. Give me a second, I'm just going to get some things off my screen right now. Okay, so let's draw some forces on this diagram. We've got a 6G acting down, we've got tension acting up. We've got a normal reaction R. We've got 15G acting down. We've got the tension acting this way, and we've got friction acting that way. So, part A. If we resolve on the 15 kg this way, we can see, because it's an equilibrium, I think we're going to have T will equal the FR. And on the 6 kg, if we resolve upwards, we'll have T will equal 6G. So therefore, our friction must be equal to 6G because T equals 6G as well. You can multiply 6 by 9.8 if you really want to find the actual numerical value. I'm going to leave it like that. So part B, given instead the contact force between A and the table is smooth, find the acceleration system and the tension in the string. So we don't have any more friction now for the second part. So on the 15 kg, we're going to have the resultant force, which is the mass times acceleration, will equal the tension in this case. It's the only force acting parallel to the plane that way. So we know that 15A equals T. On the 6 kg, we resolve that way because we're going to be accelerating that way. Let's use a 6A because mass times acceleration will equal our resultant force, which is going to be everything the same direction minus everything in the opposite direction, which is 6G minus T. So if we add 1 and 2 together, okay, these two equations, call that equation 2, 15A plus 6A gives me 21A. Add the t's, they cancel, so that leaves me just 6G on the right hand side. Scroll down to some space. So therefore A will equal 6G over 21 meters per second squared. And now if we substitute that into 1, okay, then what we get is we get 15 times 6G over 21 will equal T. And when you calculate that all out, you'll get 30G over 7 newtons. Which I think comes out to a nice value. It actually comes out to 42 newtons if you calculated it. Right, no questions coming. So, question 4, here you go. It's draw a diagram, so let's just give you 5 minutes to work this one out. I'll stop at 1 minute. Okay, so let's look at this question. Put our normal reaction in. Our weight is 7g. Our tension is T. Tension of T. And we've got a weight of mg on this. So we know that tension equals 18.2 newtons. And I'm just going to check it and see if it's in equilibrium. It doesn't appear to be in equilibrium. So the ball starts to move downwards. So we're going to accelerate this way. So if we go on the box, then the resultant force ma, which is 7a, will equal everything in the same direction as the acceleration. And the only thing we got is the tension. So it's equal to 18.2. So that gives us that the acceleration is equal to 2.6 meters per second squared. Now if we resolve on the ball, and we'll resolve downwards. So we've got ma will equal mg minus the tension, minus 18.2. Now we know a, so we know that m times 2.6 will equal m times 9.8 minus 18.2. So 18.2 will equal 9.8 m minus 2.6 m. What's that going to give us? 7.2 m on that side is 18.2. So m will equal 18.2 over 7.2. And it comes out to be 2.53 kilograms to 3SF. Okay. Right. Let me just have a look. I'm trying to work out how many questions we got left. I think the next question's quite a straightforward one. And if you've got the notebook, you'll notice there's some answer sheets as well, which I'm using for my own answers. Which you can scroll down. I've done the next question, question 5. But I want you to have a go at question 7 to finish off. And this, I'm sure, will be well, it doesn't take very long to do if you know what to do, but you might need to think a little bit. So I'll give you 5 minutes to do this question. 1 minute to go.